Finally, we're going to see a real application, a really useful application, that is. It is tuning your guitar. The abstraction of the problem is that you have a reference sinusoid at some frequency omega naught, you have a tunable sinusoid of frequency omega, and we would like to make omega and omega naught as close as possible, actually equal, and this only by listening to it. And what we are going to hear is a beating between these two frequencies when they are close enough, and then by tuning we can bring this beating to essentially frequency 0, at what point omega is equal to omega naught, and we have tuned our guitar string with respect to a reference frequency. So how are we going to go about this? Well, first we bring omega close to omega naught. That's sort of easy if you have a minimum of musical ear. When these two frequencies are close, we play both sinusoids together. Then we have to remember trigonometry, and we write xn, which is a sum of cos omega naught n plus cos of omega n, in terms of a sum and a difference of these two frequencies, which finally can be written approximately as 2 times the cos of the difference, delta of omega, times n, and the cosine of the base frequency omega naught. From this formula, we see there are 2 components. There is the error signal, the cosine of delta omega n, and there is a modulation signal, the cosine at omega naught. When omega is close to omega naught, the error signal is very low frequency, so we cannot really hear it because it's such a low frequency. So the modulation will bring it up to the hearing range, and we're going to actually hear it as an oscillation of the carrier frequency. And we're going to see this pictorially in just a moment. Let's look at the pictorial demonstration here. So we start, omega 0 is 2 pi times 0.2, omega is 2 pi times 0.22. The difference, which is actually half of the difference between the two, is 2 pi times 0.01. We see now, interestingly, we have the carrier frequency, which is a red curve, modulated by the difference, by cosine of delta of omega. So we see this, the beating in blue, overlaid to the red curve, which is modulation. We can change the frequency omega to 0.21 times 2 pi. The difference now is 0.005. The beating is slower. We pick omega is equal to 2 pi times 0.205. The beating is even slower. And here we take an example where omega is very close to omega naught, and the beating is extremely slow, and we almost see only the modulating frequency omega naught and a very slow variation due to the beating by cosine of delta of omega. It's time to see a video demonstration how to tune a guitar using this very simple principle. You probably have seen musicians do it on stage. Now you understand the math behind it. Okay, after all these math, let's try to do something useful, like tuning an electric bass. An electric bass has an E string, which is a frequency of 41.2 Hz, and A string, which has a frequency of 55 Hz. To use the result we have just seen, we want to find 2 frequencies that we want to make equal. As long as they are not, there will be a beating that we can adjust. We're going to hear this in just a moment. So the first harmonic of the E string here is at 83.4 Hz. The third harmonic is at 164.8. For the A string, the first harmonic is at 110, and the second harmonic is at 165. And we're going to use these 2 harmonics to do the tuning, and you can hear when they are out of tune, there is a beating. And as you get them closer and closer, the beating slows until it's actually 0 beating, and then the 2 frequencies are similar, and then we can start playing something like, or something else.